Okay, students, so let's start with the past paper questions of pressure. This is applicable for O levels and IGCSE physics both, and these are theory questions. A fixed mass of gas in a glass tube is trapped by a seal at one end of the tube and by a column of mercury. The mercury is free to move within the tube. Okay. The tube is rotated slowly from the vertical as shown in figure 3.1 to the horizontal as shown in figure 3.2. So this is the vertical position and this is the horizontal position. Simple as that. Okay. The volume of the gas increases and its temperatures remain. The tube is rotated slowly. Okay. So as the tube is getting rotated from vertical to horizontal, the volume of the gas increases and the temperature remains constant. Whenever the temperature is remaining constant, always remember Boyle's law gets applied. Pressure is inversely proportional to volume. Okay. Describe why rotating the tube changes the pressure of the gas in the sealed end. Okay, why does rotating the tube changes the pressure of the gas? Initially, can you see the gas had this amount of volume? And after you rotate it horizontally, the volume, as you can say, increased. As you rotated the tube from the vertical to the horizontal position, the volume increased. Or you can say the pressure decreased. Why is this the case? When you were in the vertical position, this mercury was applying a pressure at the gas. But as soon as you shift it to a horizontal position, mercury is no longer applying a pressure at the gas. So, how will you write this? In the vertical position, in the vertical position, in the vertical position, mercury was applying, mercury was applying a pressure at the gas, at a pressure on the gas, I would say, a pressure on the gas due to its height, due to its height, due to its height. However, however, in the vertical position, in the in the horizontal position, in the horizontal position, the height of mercury is 0, pressure due to mercury is 0, hence pressure decreases. Hence pressure decreases, volume increases. Simple as that. Let's move on to part 2. Explain using ideas about particles why pressure of the gas decreases when its volume increases. Okay. Why will the pressure decrease when the volume increases? So, first point, as volume increases, molecules will move further apart. As volume increases, molecules move further apart. Molecules move further apart. As molecules move further apart, what will happen? The collision frequency of molecules decreases. Frequency of molecules decreases. Okay. As the collision frequency of molecules decreases, what will happen? As the collision frequency of molecules decreases, what will happen? The force per unit area decreases, and as the force per unit area decreases, what will happen? The pressure decreases. The pressure decreases. Simple as that. Nothing complicated. Let's further move ahead. In figure 3.1, the length of mercury column is this. This is the height. Okay. This is the density of mercury. The atmospheric pressure is this. We have to calculate the pressure of the gas in the tube. Basically, we have to calculate the pressure at this point. So the pressure at this point will be a sum of what? You can say the pressure of gas will be a sum of what? Pressure due to mercury plus atmospheric pressure. What will be the pressure due to mercury? Density, that is 14,000, multiplied by G. Are we given the value of G here? No. The question hasn't specified the value of G. If the question doesn't specify the value of G, you will take 9.8. multiplied by height, that is 0.3, plus the atmospheric pressure, that is 1 into 10 raised to the power of 5. What does your pressure of gas come out to be? 14,000 into 9.8 into zero point 0.3 plus 10 raised to the power of 5. This comes out to be what? 141,160. If I round it off till three significant figures, 14100 pascals is your answer. Let's further move ahead. The pressure of a different sample of a gas changes at constant temperature. Okay, Boyle's law is being applied. Figure 3.3 shows one point marked X on a graph of pressure against volume for the gas sample. At X, the pressure of the gas is P naught and the volume is V naught. If you double the pressure, the volume will halve. If you double the volume, the pressure will halve. So your graph will be somewhat like this, a curve. Okay, you can draw a better curve with a pencil. Let's move on to the second question. A student pushes a drawing pin into a wooden board as shown in figure 4.1. Okay. The area of the pin in contact with the finger is this. Okay, this area is 5 into 10 raised to the power of minus 5. Okay, the student pushes downwards, and with the force of this, the mass of the drawing pin is very small. Calculate the pressure exerted by the finger on the drawing pin. So pressure is equal to what? Force over area. What is your force? 26. What is your area? 5 into 10 raised to the power of minus 5. What will your pressure come out to be? 26 divided by 5 into 10 raised to the power of minus 5. This gives you a value of 5.2. This is your area, right? This is your force. Have I raised to the power of 5.2 into 10 raised to the power of 5 pascals is your pressure. Okay. Yeah, that's great. Compare the force exerted by the finger on the drawing pin with the force exerted by the drawing pin on the wooden board. Okay, so there are two forces acting here. One that is from the finger on this pin, and one that is from the drawing pin on the wooden board, like this. Let's say this is F1 and let's say this is F2. Both of them will have the same magnitude. You can say both the forces have the same magnitude. Both the forces have the same magnitude. Have the same magnitude. Have the same magnitude. Simple as that. Let's move on to part 3. Explain why the drawing pin goes into the wooden board but not into the finger. Okay. Why does the drawing pin goes into the wooden board but not into the finger? So basically, if both the forces are same, why is the pin going into the wooden board but not into the finger? Can you observe that when the drawing pin is in contact with the finger, it has a larger area, and when it is contact with the wooden board, it has a smaller area. So how will you write it? The drawing pin, when the drawing pin is in contact, with the wooden board, is in contact with the wooden board, the area is small, resulting in a greater pressure, resulting in a greater pressure. And if your pressure is greater, what will happen? Hence the wooden pin, hence the drawing pin, hence the drawing pin goes inside the wooden board, goes inside the wooden board. Simple as that, nothing complicated. Let's move on to part B. Figure 4.2 shows water emerging from a plastic bag that contains a number of small holes. Okay. Explain why water emerges from each hole in a direction at right angles to the surface of the bag. Why does water emerges at right angles like this? Like this. Like this. So what will we say? Pressure of the water. Pressure of water acts on the bag. Pressure of water acts on the bag. And as the pressure of water acts on the bag, what will happen? This causes a force that is perpendicular perpendicular to the area of the bag, perpendicular to the area of the bag. Hence, the water emits at right angles to the surface of the bag. Simple. The hole at B and A are at the same size. Okay, so hole at A and B are of the same size. Let me erase some of these things. Examiner is trying to say the hole at A and B are of same sizes. Okay. Explain why water emerges faster from the hole at A than from the hole at B. Why is the water emerging faster from hole at A? Because can you see the hole at A is at a greater depth? Since the hole at A is a greater depth, A will experience a greater pressure. If A experiences a greater pressure, the force that A experiences will be greater. Hence, water emits out at a faster rate. So let's write all this story for 1 mark. Since A is at a greater depth, greater depth than B, the pressure, the pressure at A is greater than the pressure at B. The pressure at A is greater than the pressure at B. Hence, the force at A is also greater than the force at B, causing causing water to faster emerge faster from point A. From point A. Let's move on to the next question. Figure 3.1 shows a syringe mounted vertically in a block of wood and sealed at one end. A plunger is free to move inside the syringe. Okay, so this plunger is free to move inside the syringe. There is trapped air inside the syringe. Okay, so this is your trapped air inside the syringe. This entire thing. Okay, and okay, what else are we given? The air inside the syringe exerts a pressure on the walls of the syringe. Okay, define the term pressure. What is pressure? Pressure is force per unit area. Pressure is what? Force per unit area. Okay, let's move ahead. Explain how the air molecules in the cylinder of the syringe create a pressure. How the air molecules create a pressure. What will you write? The air molecules, the air molecules collide, collide with the walls of the syringe, with the walls of the syringe. Okay. This collision, this collision produces, or these collisions produce force, and the force per unit area, and the force per unit area gives rise to pressure. Simple. The air molecules collide with the walls of the syringe. These collisions produce force, and the force per unit area gives rise to pressure. Let's further move ahead. A 10 Newton weight is applied on the top of a plunger. Okay. The plunger moves down slowly so that the temperature of the air inside the syringe does not change. If the temperature is not changing, which type of law is this? Boyle's law. Okay. Before the weight is placed on the top of the plunger, the pressure of the air inside the syringe is this, the volume is this. Okay. The cross sectional area of the plunger is this. Okay. Calculate the pressure of the air in the syringe after the plunger stops moving. Okay. We have to calculate the pressure of the air in the syringe after the plunger stops moving. So, first of all, due to this 10 Newton weight, what will be the axis pressure? Force over area. Force is 10. Area is 1.2 into 10 raised to the power of minus 4. Let's calculate this pressure. 10 divided by 1.2 into 10 raised to the power of minus 4. This pressure comes out to be 8.33 8.3. 1 forward, 2 forward, 8.3 into 10 raised to the power of 4 pascals. Okay. This is your access pressure due to the weight. Okay. What was your initial pressure? 1 into 10 raised to the power of 5 pascal. What will your total pressure be? 8.3 into 10 raised to the power of 4 plus 1 into 10 raised to the power of 5. What will be your total pressure? Let's calculate that. Your total pressure comes out to be, one second, your total pressure comes out to be 1.83 into 10 raised to the power of 5 pascals. Okay. Calculate the volume of the air inside the syringe after the plunger stops moving. So what will we do? P1 V1 is equals to P2 V2. What is your pressure 1? 1 into 10 raised to the power of 5. What is your volume 1? 50 cm cube. What is your pressure 2? 1.83 into 10 raised to the power of into 10 raised to the power of 5. 1 second. Into 10 raised to the power of 5 into volume of 2. 1 into 10 raised to the power of 5 divided by 1.83 into 10 raised to the power of 5 into 50. What will your volume 2 come out to be? Let's calculate that. 10 raised to the power of 5 divided by answer into 50. This gives you a value of 27.3. Your volume, your final volume comes out to be 27.3 centimeter cube. Simple. Let's move on to the next question. Figure 1.1 shows a wooden bench of weight 2000 Newton. Okay, so this is a wooden bench of 2000 Newton. The weight is maybe acting somewhere here. This is your 2000 Newton. Okay. Each of the two supports have an area of 0.04 meter square. Okay, in contact with the ground. Calculate the pressure on the ground due to the bench. Okay. So this weight of 2000 Newton gets divided among the two supports. Okay. So let's say this support will be experiencing 1000 Newton. This support will be supporting 1000 Newton as well. Can you calculate the pressure? Yes, pressure is equal to force over area. What is your force on each support? 1000. What is your area of each support? 0.04. 1000 divided by 0.04. This comes out to be 25,000 pascals. Simple as that. The center of mass of the bench is 1.1 meter from the left hand of the bench and 0.24 meter from the front. Okay. So the center of mass is, let's say, 1.1 meter from here and 0.24 meters from the front. Okay. Basically, if it is from the front, I should have marked it from the back side. Let's do this. Yeah, somewhat like this. 0. Oh, actually, my drawings might trouble you guys, but please bear with that. This is 1.1 meters and this is, let's say, 0.24 meters. Yeah. Let's further move ahead. Suggest one reason why the center of mass is in this position. Why? Because it is symmetrical. It is symmetrical. 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 Symmetrical in the right left direction. Symmetrical in the right left direction. And in the forward backward direction. And in the forward backward direction. Simple as that. The center of mass is at this position because it is symmetrical in the right left direction and it is symmetrical in the forward backward direction as well. Let's further move ahead. There is a force exerted vertically downwards from the point P shown in figure 1.1. Calculate the maximum force that can be exerted vertically downwards at P without the bench rotating about point Q shown in figure 1.1. Okay. What will be the maximum force that I can apply here known as P? Known as P. And let's erase some of the things. I don't think we need this. I don't think we need this. Okay. Our pivot is what? Q. And our weight is being applied at, let's say, this is 1.1 meters. Our weight is applied exactly in the middle like this. That is 2000 Newton. This is your pivot. Q is your pivot. you have to calculate the maximum force P, okay, before the object topples. So, what would be the maximum force P? If you can observe, this weight W is causing what? This weight W is causing clockwise movements. This is a force of 2000 Newton at a distance of what? At a distance of 1.1 minus 0.5 distance. 1.1 minus 0.25 distance. That is what? 1.1 minus 0.25. This equals to 0.85. Okay. So there is a weight of 2000 Newton at a distance of 0.85. This is your clockwise moment. 2000 into 0.85. What will this answer be? 2000. This equals to 1700. This is your clockwise moment of 1700 Newton meter. This force P will generate what? Anti-clockwise moment. This force P will generate anti-clockwise moment. What will this anti-clockwise moment be equal to? Force of P. And what is the distance from the pivot? 0.25. P into 0.25. Can we equate both of them? Yes. We can say anti-clockwise moment is equals to clockwise moments. The clockwise moments were 1700. The anti-clockwise moments were P into 0.25. P comes out to be what? 1700 divided by 0.25. What will your answer be? Your answer comes out to be 6800 Newton is your maximum force that you can apply. Have I taken the measurements correctly? Yes, I guess I have taken the measurements correctly. Yes, this is the maximum force P. Let's move on to the next question. Okay. A hydraulic press is used at a recycling center to compress waste material. Figure 7.1 is a side view of the press. Okay. This is the side view of the press. Okay. A force to the left is exerted in piston 1. This is your force that is being exerted. This is your piston 1. Okay. Oil is pushed along the pipe and this moves piston 2 downward. Okay. This moves the piston 2 downwards as piston 1 is moving towards the left. Okay. Piston 2 compresses the weight. Okay. Oil is a liquid. State the property of oil that makes it suitable for use in a hydraulic system. It is incompressible. Any incompressible liquid can be used in a hydraulic system. Okay. Explain in terms of molecule why a liquid has this property. Because in a liquid, molecules are close together, and they experience large repulsive forces. In a liquid, molecules are close together and they experience large repulsive forces. Hence, they are incompressible. Okay. Let's move on to part B. Suggest one advantage of using oil as liquid in a hydraulic press. It acts as a lubricant. Okay. Let's move on to part C. The cross-sectional area of the piston is this. The piston 1 exerts a force of this on the oil. Okay, calculate the pressure on the oil due to this force. Pressure is equals to force over area. What is your force? 4500 Newton. What is your area? 0.018. Let's calculate it. 4000 divided by 0.018. This comes out to be 2.5 into 10 raised to the power of 5 pascals. Okay. The atmospheric pressure is this. You have to calculate the total pressure. Total pressure is equals to what? 10 raised to the power of 5 plus 2.5 into 10 raised to the power of 5. This comes out to be 3.5 into 10 raised to the power of 5. The area of piston 2 is in contact with the oil. Okay. The area of piston 2 that is in contact with the oil is 1.4 meter square. Initially, the upper surface of piston 2 is level with point P. Okay. So initially this surface, let me highlight this. Initially this green surface is with point P like this. Initially this green surface is with point P like this. Okay. Calculate the force exerted on piston 2. We have to calculate the force exerted on piston 2 due to the pressure calculated in C part 2. Okay. So what is force equals to? Pressure into area. What is your pressure? 3.5 into 10 raised to the power of 5. What is your area? 1.4. Multiply 3.5 by 1.4. This gives you an answer of 4.9 into 10 raised to the power of 5 Newton is your answer. Let's further move ahead. Piston 1 moves along the pipe. Okay. The pressure of the oil in the pipe at point P remains constant. Okay. So the pressure here at point P remains constant. Okay. What else is the examiner saying? Let's see that. Come here. Piston 2 moves downwards. Okay. The pressure of the oil at the upper surface of piston 2 increases. Oh, very good. So basically, the pressure at the upper surface that was initially at point P, if it starts moving downwards, the pressure will increase. And that's perfectly fine. Why? Because if the upper surface starts moving downwards, what will happen? The depth of oil increases. If the depth of oil increases, the pressure will increase. So let's see what the examiner is asking. Explain why the pressure at the upper surface of piston 2 increases. Very easy. The pressure of oil, the pressure of oil is equal to the product is equals to the product of what? Is equals to the product of density G and depth. As depth increases, as depth increases, your pressure of oil increases. Simple. Let's move on to part 2. The density of the oil is this. The upper surface of the piston is now at a depth of this. This is your density. Calculate the increase in force exerted at the upper surface of piston 2 by the oil. Okay. So do you remember force is equals to pressure into area? What will be your added pressure? Pressure will be rho g into change in height. What is your area of piston 2? You know that the area of piston 2 was provided to you in the previous part, that is 1.4 meter square. So let's multiply that as well. What is your density? 900. Okay. Multiplied by g. Are we given the value of g? Yes, 10. Multiplied by what is the height? 0.5. Multiplied by 1.4. Can we calculate the increase in force? Yes. 900 into 10. This is 9000 multiplied by zero point 0.5 into 1.4. This comes out to be 6300 Newton is your answer. Simple as that. Let's further move ahead. The air is trapped in the plastic bag that contains the waste. The temperature of the air in the bags remain constant. That means Boyle's law is being applied. Okay. Boyle's law applied. Explain in terms of molecules why the pressure of the trapped air increases as it gets compressed or volume decreases. This I have done many times in the video as well. Scroll, you can scroll back and see the answer as well. Also, I have written a detailed answer to this in the notes, so you can view the lecture video as well. So, yeah, this is pretty much repeatedly done. So, let's leave it. Let's move on to the more difficult question. Let's see this. The density of water in a lake is 1000. At a depth of 25 meter, the surface of the lake, the total pressure is this. Okay. What is meant by pressure? Force per unit area. Already did this. I guess I remember in a question. Force per unit area. The gravitational field strength is 10. The pressure due to 25 meter of water. Very, very easy. Pressure is equals to rho g h. Rho is 1000. G is 10. Your height is 25. So your answer will come out to be 25 into 10 into 1000. This comes out to be 2.5 into 10 raised to the power of 5 pascals. What is your atmospheric pressure? When you subtract both of these pressures, you will get the atmospheric pressure. 3.5 into 10 raised to the power of 5 minus 2.5 into 10 raised to the power of 5. This gives you your atmospheric pressure of 1 into 10 raised to the power of 5 pascals. Let's see this. The diagram here is slightly erased because these are scanned documents. So, yeah, these are scanned documents. So, it is possible that some diagrams might be erased. Let me make, yeah, this is the thing. I hope I did justice to the diagram. An underwater depth gauge contains a small cylinder as shown in figure 8.1. Gas is trapped inside the cylinder by a piston. Okay, the piston is free to move. This is your gas. This is your gas. Okay. Now, what will happen? Let's see. The outer surface of the piston is in contact with the water. Okay. As the depth gauge is lowered into the water, the piston moves into the cylinder. The This moves the needle on the dial to indicate the depth of the gauge in the water. Okay. So as we move this inside the water, the piston moves inward. Okay. Explain why the piston moves into the cylinder. Very, very easy. Why does the piston move into the cylinder? Because the outward pressure, the outward pressure, you can say because the outward pressure exceeds the inward gas pressure, or you can further say something like this: as the outside force increases, as the outside force is greater, as the outside force becomes greater compared to the inward force, compared to the inward force, inward force, the piston moves inwards due to a resultant resultant force. Simple as that. And you can also state the direction of this resultant force, that this resultant force is acting inwards because the outward force is greater. Let's move on to part 2. The temperature of the gas does not change as the piston moves into the cylinder. Now, see how repeated this question is. This is irritating. This is an FAQ that we have done in the notes as well, in the video as well. You can scroll back. At the surface of water, the volume of the trapped gas is V naught. Okay. At the surface of water, the volume of the trapped gas is V naught. On figure 8.2, sketch a graph to show how the volume of the trapped gas decreases as the gauge is lowered into the water. As the gauge is lowered into the water, what will happen? Pressure will increase. As the pressure keeps on increasing, your volume will decrease. So as you move to deeper and deeper, your volume will decrease like this. This is your answer. Simple. Let's move ahead. The instructions for the depth gauge state that each time it is used, the needle of the dial must be reset to zero at the surface of water. Suggest one reason for this. You, this allows you to measure, this allows you to measure pressures at different atmospheric. This allows you to cater. I would say this is a wrong wording. I would say this allows the depth gauge to cater for, what? To cater for different atmospheric pressures. To cater for different atmospheric pressures. Simple as that, nothing complicated here. Let's further move ahead. The density of the air trapped in the gauge increases. The density of the water remains constant. Why? Because water is a liquid. Explain in terms of molecules of water why the density of water remains constant. Firstly, because molecules are close together. And secondly, why? Secondly, because there are large repulsive forces between the molecules. Large repulsive forces between the molecules. Simple as that. Between the molecules. That's why water or liquid doesn't compress. Simple. Let's move on to the next question. Figure 1.1 shows a tube full of mercury placed upside down in a dish of mercury. Initially, a small piece of mercury closes the open end of the tube. This is the open end of the tube. The piece of glass is removed and the level of mercury in the inverted tube falls. Okay, can you see initially this was the level, this has fallen. Okay, explain why the level of mercury in the tube falls. How can you explain this? The level of mercury in the tube falls. Why? Because the pressure of mercury the pressure of mercury in the inverted test tube, in the inverted test tube is much greater, much greater than the atmospheric pressure, than the atmospheric pressure. Hence, hence some of the mercury flows out. Hence, some of the mercury flows out. Mercury flows out. Okay. State what is found at point X in figure 1.2. This is a vacuum. Simple. You can write it here. This is a vacuum. Okay. Describe how the tube of mercury in figure 1.2 is used to determine a value for the atmospheric pressure in pascals. Okay. How can you determine a value for atmospheric pressure using figure 1.2? First of all, you will measure this height h using a meter rule. You will say measure this height using a meter rule. Let's write it. Measure the height of mercury. Measure the height h of mercury. Measure the height h of mercury above the fluid. Above the fluid. Using a meter rule. Using a meter rule. This will probably get you 2 marks. Third marks. How will you get the third marks? Apply the formula. Apply the formula. Pressure is equals to rho gh to get the atmospheric pressure. To get the atmospheric pressure. This is a 3-marker question. First 2 marks lie in the first point. The third marks lie in the second point. This marks the end of the past papers for pressure. If you have any questions, you can ask.